Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about causal inference, which is the problem of determining whether a certain treatment, for example a medicine, has a causal effect on an outcome of interest, for example whether a patient recovers. Interestingly, effects that are observed in the data do not necessarily reflect causal effects. It's possible for a medicine that is useless to seem very effective in practice. We're going to understand why that can be the case and how to avoid it using randomization. We're also going to talk about confounding factors which distort the observed effects in the data, and we're going to learn how to correct for them. Let's get to it. So we're going to talk about causal inference, and two very important concepts are potential outcomes and confounders. Our goal here is to determine whether a certain treatment has a causal effect. For example, whether a new drug cures a disease. Imagine that we have some data from a study where we're trying to evaluate a drug. So we have a treatment T that is represented by a random variable T, which tells us whether the patient received the drug, in that case T is equal to 1, or they did not receive the drug, in that case T is equal to 0. And then we have the outcome of interest, which is whether the patient recovered, in that case y is equal to 1, or not, y is equal to 0. We want to determine whether giving the medicine actually causes patients to recover. Typically, in studies to evaluate drugs, you have the control group where you don't give the medicine, and you have the treatment group where you do give the medicine. Here we see that in the control group, there's one happy face and 3 sad faces. Happy face means they recover, sad face, they do not recover. So the probability of recovering, given that you're in the control group, is 25%. And in the treatment group, there's 3 happy faces and 1 sad face. So the probability of recovering if you're in the treatment group is 75%, which is much higher. So you might think that there's an effect here, like the drug seems to be effective. So a natural question is, does this imply that a new patient is more likely to recover if we treat them with the drug? And the answer is not necessarily. And that's the whole point of this video. We're going to see why. In order to see why, we're going to define potential outcomes. Then we're going to see how randomization avoids this distortion in observed effects. Then we're going to talk about confounding factors and how to adjust for confounding factors. What are potential outcomes? Potential outcomes are a key concept in causal inference that enable us to define causal effects formally. Potential outcomes represent alternative scenarios that are defined for all patients. What do we mean by that? We have a scenario where every patient is untreated. No one receives the medicine. And this is going to be defined even for patients that do receive the treatment. It's just hypothetical at some point. So here we're going to indicate by PO0, this is a random variable that corresponds to the potential outcome of not receiving the treatment. PO0 being equal to 1 means that a patient would have recovered if they had not received the medicine, and this is regardless whether they received the medicine or not. If PO0, the potential outcome associated to not treatment, is 0, then that means that the patient would not have recovered if they did not receive the medicine. And again, this is defined regardless whether they received the medicine or not. In particular, it is defined for patients that did receive the medicine, and that's the key thing that we need to understand. Conversely, we have the potential outcome associated with treatment that tells us what would have happened if the patient was treated, regardless whether they were treated or not. Okay, so you can already see that we're not going to be able to perhaps observe all of this because we don't have 2 alternative realities that we can observe where everyone was treated and everyone was untreated. However, in causal inference, in order to define causal effects, we pretend like we could have access to those 2 alternative realities. So if the potential outcome associated with treatment is equal to 1, that means the patient would recover if they received the treatment. If the potential outcome associated with treatment is equal to 0, that means the patient would not recover if they received the treatment. So now we can define causal effects formally. The drug is going to have a causal effect if the probability that patients recover in this alternative reality where everyone receives treatment is higher than in the alternative reality where no one receives treatment. Let's take a look at an illustration of this. Here, this is the alternative reality where no one receives treatment, and it turns out that 25% of the people recover. Now we go to the alternative reality where everyone receives treatment, and there 75% of the people recover because there's these two sad faces there. This means that if, like, the difference between giving the medicine to everyone and not giving the medicine to everyone is 0.5. There's a huge difference. There's a huge causal effect of giving the medicine. This is another example where there is no causal effect. If in the alternative reality where nobody receives the treatment, 50% of the people recover, 50% of the people do not recover. In the alternative reality where we give everyone the treatment, the same is the case, okay? Like 50% recover, 50% don't recover. Mathematically, the probability that the potential outcome associated with no treatment is 0.5. The probability that the potential outcome associated with no treatment is equal to 1. That probability is equal to 0.5. For the potential outcome associated to treatment, it's also 0.5. So basically, this means that if we give the medicine to everyone, 50% of the people are going to recover. If we don't give the medicine to everyone, 50% of the people are going to recover anyway. So there's no causal effect of the drug. This in contrast to the previous example where there was a causal effect. So now we're able to define causal effects. Are we done here? And this is a good moment to stop the video and see whether you understand the concept of potential outcomes and why we are not done at all. So the reason why we're not done at all is the fundamental problem of causal inference. Both potential outcomes are defined for every patient, right? We could go to the alternative reality to where the patient is treated, and we could go to the alternative reality where the patient is not treated. But this is only true mathematically. In practice, we're going to either treat the patient or not. So we are only going to have access to one of these realities. The other one is going to be counterfactual. It's going to be counter to factual reality. It will not exist. So we do not get to see it. The treatment T determines which of the two potential outcomes we are going to observe. If T is equal to 0, the observed outcome Y is going to be equal to the potential outcome associated with no treatment. If T is equal to 1, the observed outcome, the outcome that we actually get to see, is going to be the potential outcome associated with treatment. Okay, so let's go to a situation where the drug does not work at all. Okay, as you can see, these are different patients. This guy recovers if they don't receive the drug. They also recover if they receive the drug. This patient does not recover if they don't receive the drug. This patient, like the same patient, recovers if they receive the drug. So when we have access to these two alternative realities, what we see is that the drug doesn't make any difference. The potential outcomes being equal to 1, that probability is equal to 0.5 for both potential outcomes. No causal effect. But now in reality, we have to treat some people and not treat some people in order to see whether the medicine works or not. And this is what we decide to do. We decide to treat these people, and to not treat these people. And here, I want you to see whether the people that we're treating are the same as the people that we're not treating. Take a little moment to look at this. What you may notice is that we're treating patients that would recover anyways more. There's 3 of those in the green. Maybe I'll change the color. There's 3 of those in green, more than the ones that do not recover. And if we look at the patients that we did not treat, among those there are more of these sad patients that do not recover. Wait, I got confused there. Sorry, this was wrong. I was looking at this guy, okay? That guy was treated and they were going to not recover regardless. But the point stands. If you look at the people that were not treated among those, that includes more of the people that were not going to recover anyway. You might think that this is kind of strange. Why would that happen? Actually, this can happen very easily. For example, where people used to evaluate surgeries, what happens is that you cannot perform a surgery on someone that is not healthy enough. So the groups that were treated with surgery back in the day when there was no randomization tended to be healthier than the people who did not receive surgery, because that included many people that could not receive surgery because they were not healthy enough. So it's not that strange that a healthier group might receive the treatment in contrast to a group that is less healthy. Let's see what happens when that is the case. Well, now, here we have access to the two alternative realities because these are my slides, okay? And I made up this example. But in reality, for the patients that we decide to treat, we're not going to see the potential outcomes associated with no treatment. We're just not going to see them. And for the patients that we decide to not treat, we're not going to know what would have happened if we had treated them. We will not know the potential outcome associated with treatment. That's just life. It is what it is. It's the fundamental problem of causal inference. These guys that are now missing are counterfactuals that we do not have access to. When we build our control and our treatment groups, we're not going to have access to those counterfactuals. And now we're just going to have to count how many happy faces are in the control group and how many faces are in the treatment group. But you might already be seeing that we're going to have a problem because we systematically put people that were less healthy in the control group. So now we realize that only 25% of the people in the control group recover, but that's not because the drug worked. It's because of how we selected who was in the control group. And when we look at the treatment group, we realize that 75% of the people in the treatment group recover, not because the drug was effective. We know that it wasn't because I made up this example, but rather because of how we selected people for treatment. And that's why we cannot trust observed effects in the data. Here, like the probability of y being equal to 1, given this should be equal to 1, given that the treatment is 0 is 0.75, given that the treatment is 0.25, the probability of y being equal to 1 given that the treatment is 1 is 0.75. Those are very different from the true probabilities that the potential outcomes are equal to 1, which are the same with and without treatment. The medicine is actually useless, but it seems effective. How do we avoid this? We can avoid this through randomization. So here the key is that when we see the observed outcome, we would like it to be representative of the potential outcome. If we look at the probability that the potential outcome associated with no treatment is equal to 1, we would like that to be equal to the probability that the observed outcome is equal to 1 within the control group, within the people that were not treated. But unfortunately, what we actually get to see is the potential outcome associated with no treatment conditioned on who we're putting into the control group. So conditioned on being in the control group, not receiving treatment. And this can severely distort the observed effects, as we saw in our example. Same thing for the potential outcome associated with treatment. We would like it to be equal to the observed outcome given treatment, but that observed outcome given treatment is the potential outcome associated to treatment conditioned on being in the treatment group. So if systematically we're putting healthier people in the treatment group, we're not going to get a good estimate of the potential outcome associated with treatment. So what do we need? Oh, actually, I should have asked you this. Maybe you didn't read it, so think about it anyways. When is the observed outcome representative of the potential outcomes? When do we have equality here? Okay, because this is not equal in general. When is it equal? It's equal if conditioning on the treatment does not make any difference, which means that the control group and the treatment group have the same distribution, right? In that case, if the potential outcomes are independent from the treatment, then this equality holds, and the observed effects are going to actually be representative of the causal effects. So we need the treatment and the potential outcomes to be independent. The first time you hear this, you're like, wait a minute. How can the outcome be independent from the treatment? Because, for example, it's possible that the medicine actually works. Yeah, true. But we're not saying that the observed outcome has to be independent from the treatment. Not at all. We're saying that the individual potential outcomes need to be independent from the treatment. What this prevents is us putting people that are more likely to recover regardless of treatment into the treatment group, like systematically putting healthier people in the treatment group or systematically healthier people in the control group. This is what this is avoiding. What's important to remember is that here we're talking about independence between the treatment and outcomes in these two alternative realities. Of course, the observed outcome is typically going to be very dependent on the treatment. We're talking about the potential outcomes. The proportion, what we're trying to guarantee is that the proportion of, for example, healthy patients in the control and the treatment groups is the same as in the whole population. If that is the case, then we're going to be able to observe the true causal effects. So in our example, as we already talked about a little bit before, when we look at the people that were treated, they were clearly more healthy in general than the people that were not treated. So clearly here, the treatment and the potential outcomes are very dependent. And that's why we didn't observe the true causal effect. So how can we guarantee independence between the treatment and the potential outcome? Well, we need to make the treatment independent from how healthy or not healthy and whatever other factors that might be different in the different patients. And a way to guarantee this is to just assign the treatment at random. It's as simple as that. So what we're going to do here is we're going to flip a coin. We're not going to look at the patient. We're going to flip a coin, and that coin is going to decide whether the patient gets treated or not. First patient, tails, not treated. Second patient, tails, not treated. Third patient, heads, not treated. Tails, not treated. Tails, not treated. Heads, treated. Heads, treated. Heads, treated. So this looks a little bit like a game. This doesn't look very serious. This is exactly what is done in practice when we do randomized controlled trials for drugs. Precisely because we want to be able to identify causal effects. So now that we've done this, it's very unlikely that systematically we've put more healthier people in the treatment group as long as we have enough data. Okay. Again, we have this effect. This effect. We have this reality where we observe what we observe. Like for the people that were treated, we only get the potential outcome associated with treatment. And for the people that we didn't treat, we get the potential outcome associated with no treatment. But now they're not systematically different, these two groups, because of the fact that we have just randomly assigned people. And thanks to that, now when we don't observe the other potential outcome, it's not problematic because the control group is representative of the whole population, and hence the observed probability of y being equal to 1 if the treatment is 0 is 0.5, and the treatment group is also representative of the whole population, so the observed probability of y being equal to 1 given that t is equal to 1 is also 0.5. Of course, if we have enough patients, so that, because if we have like very, very few patients, you could have some issues because of sample size. Here I'm assuming that you have enough patients, and that can be quantified using p-values and confidence intervals and so on. So we're not going to worry about that. So long story short, randomization enables you to ensure that the control and the treatment groups are going to have populations that are representative of the general population and are not going to be systematically different in a way that distorts the observed effects. And in particular, in our example, we realize that the drug is useless because we have randomized the treatment. If we hadn't randomized the treatment, as before, we would think that the drug is actually useful. And this used to happen all the time before people came up with randomized controlled trials. Nowadays, whenever we test a drug, we do this. We flip these coins and we decide who belongs to the control group and who belongs to the treatment group. And people in the control group typically receive a placebo, so even they don't know whether they're in the treatment group or the control group. This is exactly what they did for the COVID-19 vaccine, or one of the COVID-19 vaccines. There were 43,448 patients that were randomly divided into a treatment group that contained essentially half, and a control group that also contained essentially half. See that here the sample size is very large, so we're not worried about sample size issues. And in the treatment group, the people who received the vaccine, there were 8 cases of COVID-19, so 0.037%. Among the people, and that tells us that the probability, here I should put y equals 1, so getting COVID, given that you received the vaccine, was 0.037%. Among the control group, 162 people had COVID, so 0.746%. This is the probability of getting COVID if you did not receive the vaccine. It's much, 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 much higher. Does this guarantee that the vaccine works? Yes, because we have randomized. So this means that the two populations in the control group and in the treatment group are a representative of the general population, so that we can guarantee that the potential outcome associated with receiving the vaccine, the probability of having COVID for that potential outcome is lower than the potential outcome, that the probability of the potential outcome when you do not receive the vaccine being equal to 1. Okay, I said that in a bit of a contrived way. Basically, the vaccine works. If we were going to look at the two alternative realities, in the two alternative realities, we would observe the same thing. We would observe that a lot more people would get COVID here than here, because we have randomized. That's the key observation here. Perfect. So now we're going to talk about confounding factors. A confounding factor or confounder is a variable that governs the dependence between the treatment and the potential outcomes. We have seen that this dependence is problematic because it's the one that distorts the effects observed from the data. In our example, like in our drug example, age could be a confounder because sometimes old people don't want to take medicines. So maybe we're treating younger people more than old people. We're going to assume in our example that half the patients in the population are young and half the patients in the population are old, in the general population. So the probability of being old and the probability of being young is just 0.5. These are our young patients. They're very healthy. They would recover no matter what happens, whether you give them the medicine or not. So to be clear, these are the potential outcomes associated with no medicine. They all recover, these young patients. If we give them the medicine, they also recover. So for them, the potential outcomes are always equal to 1 because they always recover. If we condition on young, if we restrict ourselves to just the young population, they recover all the time. The probability that the potential outcomes are equal to 1 is equal to 1 for both potential outcomes. Now, for these young people, there's no causal effect. It doesn't matter whether they take the medicine or not, they're going to recover anyways. For the old patients, there is a causal effect, and we see that when we compare the potential outcome. These old people have like a top hat instead of a cap. I had to come up with these emojis by myself using LaTeX, so that's why they're quite rudimentary. So when we look at the potential outcome associated with no drug, we see more sad faces than when they do receive the drug. Okay? In particular, if you want, the drug actually there's a bunch of people, like here, this guy, that are cured in the alternative reality where they receive the drug. They're not cured in the alternative reality where they do not receive the drug. So for all patients, we see that no one recovers if they don't receive the medicine, and half of them recover if they do receive the medicine. The medicine has a strong causal effect. All right? But now we're interested in the overall causal effect. We're going to see what happens when we have a population that includes young people and old people. And young people and old people are just an example. This could also have been men and women, different races, different socioeconomic status. There's many variables that can act as confounding factors. And what we want to determine at the end of the day is the overall causal effect of the drug. How do we compute the overall causal effect for this example that we have here? Well, we can just do the law of total probability. We're going to see the intersection between being young and recovering. This is one event, and the other event that is of interest to us is being old and recovering, because the union of these two events, which are disjoint, is the event of interest, which is this person recovers when they don't receive the treatment. Okay, this is provided they don't receive in the alternative reality where they don't receive the treatment. Here we can just apply the chain rule. We know that the probability of being young and being old is 0.5. We know that the young people always recover and the old people never recover. So this is just equal to 0.5. This is the true probability that you recover if you don't receive the drug within this population, if we had access to the alternative reality where no one receives the drug. What about if everyone receives the drug? Then we have exactly the same reasoning, except that now we're looking at the potential outcome associated with treatment. We again apply law of total probability and the chain rule, but now nothing changes for the young patients because they recover anyways. But now we have that half of the old patients are recovering, the ones that when they receive the drug. So there is this causal effect that takes the probability of recovering when you receive the drug to 0.75. This is what we would like to observe from the data in order to be able to estimate the true causal effect accurately. But now, what often happens is the following. So first of all, we have seen that the potential outcomes and the age are dependent. Young people are healthier, they tend to recover more regardless of whether they take the medicine or not, in both alternative realities where they don't take the medicine or they take the medicine, compared to the old people. So now, if treatment and age are dependent, if we're treating different ages differently, then that is going to induce a dependence. So, for example, the percentage of people within the control group that are young is not half, as in the general population, and the percentage of young people that are in the treatment group is not half, as in the general population. If this happens, then that is going to induce a dependence between the treatment and the potential outcomes, which is problematic because, for example, if there are more young people in the treatment group, we're going to think that the medicine is more effective than it really is. And this is exactly what we're going to see, by the way, spoiler alert. So now we're going to assume conditional independence between the treatment and the potential outcomes given age. This is very important. This assumption means that if we restrict ourselves to young people and if we restrict ourselves to old people, there are no additional confounding factors. We're actually seeing representative samples of the population of the young people and the old people. There's nothing else that affects whether they receive treatment or not. It's a little bit as if, no, it's equivalent to having mini randomized trials for old people and mini randomized trials for young people. Of course, this is a stretch, although maybe if you're combining randomized trial data, this could be true, but this is the assumption we make to analyze the effect of just this confounder. If all of the dependence between the potential outcomes and the treatment is captured by this confounding variable, then this is what happens. So now let's take a look at the actual observed probability of recovery given that you don't receive treatment. This is equal to the potential outcome associated with no treatment, but conditioned on being in the control group, conditioned on not having received the treatment. So now we're going to separate, again by the law of total probability, between young and old people, and we're going to apply the chain rule and and also our assumption of conditional independence between the treatment and the potential outcomes given age. So here, because I'm conditioning on age, now I no longer, like the treatment is no longer relevant once I condition on age, because of this assumption that for the ages I do have like representative populations within each age. This is a very strong assumption, but again, we're just trying to capture what is the effect of this single confounding variable. Now I'm left with the probability of being young given that you are in the control group times the probability of the potential outcome associated with no treatment being equal to 1 if you're young. Okay, because again, between the young people, we assume that there's no systematic difference between the treatment and the control group. And now, this in the same way, sorry, I got a little bit stuck there for a moment. This is the probability of being old given that you're in the control group, and this is the probability that you recover when you don't receive treatment if you're old. Remember that this is equal to 1 and this is equal to 0. So we're left with this probability of being young given that you belong to the control group. This is the observed effect. And now you can see that if the probability of being young given that you're in control group is higher, the observed effectiveness of the drug, let me get this right, is lower, because you're going to see that people that are in the control group recover really, really well, but that's just because they're young, okay? The same thing is, something very similar is going to happen for the treatment group. If we condition on treatment being equal to 1, in that case, we see the potential outcome associated with 1, but conditioned on treatment being equal to 1. Again, law of total probability, and here we're applying both the law of total probability and the conditional independence assumption. And when we do that, this is still equal to 1, but this is now equal to 0.5. The important thing is that they're multiplied by the probability of being young, given that you're in the treatment group, and the probability of being old, given that you're in the treatment group. So if we put only young people in the treatment group, all of them are going to recover. It's going to seem that the drug always works. If we only put old people in the treatment group, we're going to see that only half of them recover. We're going to think that the drug does not work. But this is just because of the fraction of old against young people that we're putting in the treatment group or the control group. So as you can see, this confounding variable completely distorts the observed effectiveness of the drug. It's completely distorted. So let's look at an example where we happen to put, so among the control group, there's 1/4 of young people, and in the treatment group, 75% of them are young people. And again, this is not so strange, right? If we were just allowed anyone to take the medicine if they wanted to, it's possible that young people would decide to take the medicine, and old people are like, no, I don't want to take the medicine, or I don't want to go down to the doctor. You know, for many reasons, these systematic differences arise in reality all the time. So if that is the case, according to our calculations, the probability of recovering given that you did not receive the treatment is going to be equal to 25%. And because remember that none of the old people recover and the young people all recover, but there's only 25% of them in the control group. And the probability of recovering if you're in the treatment group now is equal to this probability of being young if you're in the control group, because all of them recover. So that is 0.75 plus the probability of being old times the rate at which the old people recover, and that gives you 0.875. So the drug seems much more effective than it actually is. Okay. In fact, what we should observe is this is the observed effect, and what we should observe is 0.5 and 0.75. The problem is we're putting more young people in the treatment group, so then the drug seems more effective. Let's take a look at a picture. This is our whole population of our young people and our old people. Again, realize that the young people recover no matter what. The old people recover more if they receive the medicine. Now we tend to treat the young people more than the old people, right? Look at the old people that are treated. There's only 2 of them. Again, we tend to put the old people in the control group, and many less young people in the control group. So then when we look at the actual data that we observe, now we don't have access to these 2 alternative realities when we see what happens if people get treated and if people don't get treated. We only get access to the actual data, not to the counterfactuals. What happens is that the control group has 2 young people and many more old people, and the treatment group, so then the observed effect as we compute it is 1/4, right? Because 1/4 of the control group is young people, and the young people always recover no matter what, and the old people, if you don't give them the medicine, they don't recover. And then for the treatment, there's many more young people, they all recover, so that's going to push up the seemingly effectiveness of the drug because there's more than half, right? 75% of them are young. And then you have these 2 old people, and one of them recovers and the other one not, because we know that the rate of recovery for old people if they receive the medicine is 50%. So that's what gives us this exaggerated effect because of how we have selected who goes into the control group and who goes into the treatment group. If we had done a randomized controlled trial, then automatically, because the selection is random and independent of age, we would have put 50% of people in the 50% of young people in the control. So the control, I got that backwards. Let me repeat that. In the control group, 50% of the people would be young because 50% of the people are young in the population. So as long as the sample size is not too small, there's going to be roughly 0.5. Like the probability that you're young if you're in control group is going to be 0.5. Same for the treatment group. We're going to have 50% of young people in the treatment group. And then if you compute the observed outcome in the control group, it's actually going to be exactly equal to 0.5 because the proportions of old people and young people are the same as in the general population. Same thing for the treatment group. We're going to see the true effect because of the fact that we have half young people and half old people in the treatment group. So that's, how randomization enables us to see the causal effect and automatically controls for the confounder. So is this the end of the story? Not quite. So this is a solved problem if you have access to randomization. It's true that randomization neutralizes all confounders, even if they are unknown, and that's why we use it in randomized controlled trials, and that's why we know the COVID-19 vaccine works. The problem is that randomization is very costly, and often it's not possible. So imagine that you want to figure out if helmets actually prevent you from getting concussions if you play American football. You're not going to do a randomized trial where you're going to have kids playing without helmets. This would not be okay for ethical reasons. You're not going to make pregnant women smoke to determine whether smoking is bad for the baby. So the solution here, the practical solution, is to correct for known confounders. If the treatment is conditionally independent of the potential outcomes given the confounder, we can correct for a confounder, but I want to remind you that this is a pretty strong assumption. This is kind of assuming that you have mini randomized controlled trials for each value of your confounder. So this assumes 1, you know the confounder, and 2, within the subgroups determined by the confounder, you have mini randomized trials, which is never going to be the case. However, controlling for the effect of a confounder is always better than not controlling. Okay, so pragmatically, you want to at least try to control for confounders, even if you know the assumptions are not going to completely hold. But how do you do that? Well, when we have this assumption, so here we have the observed treatment given the confounder, which is age in our case, and the treatment. When the treatment is 0, then we observe the potential outcome associated with no treatment, and because of the conditional independence assumption, that is the same as the probability of the potential outcome associated with no treatment, regardless of whether the patient is actually treated or not. And this is what captures the fact that if we fix the value of A, this independence assumption holds, and we have this randomization assumption where the observed effect is the effect that we're actually going to, that is a true causal effect. The same happens when we condition on treatment. Okay, we're again going to see the true potential outcome associated to treatment, but conditioned on that value of the confounder. So we are observing true conditional causal effects within each group determined by the confounder. So now it's natural to try to estimate the aggregate causal effect by combining these true conditional causal effects. So the idea now is that by the law of total probability and the chain rule, we have, or the law of total probability actually, we have that we can aggregate the probability that you don't recover given that you belong to different ages, multiplying by the probability of belonging to those ages. As long as these guys can be observed, from the data, then you're going to be able to reconstruct that under these strong assumptions that you have, like, again, mini randomized trials for each of the different ages. And the same for the potential outcome associated with treatment. You're going to take the observed probability of recovering given each age and given that you receive treatment, and you're going to combine them. So now compare this adjusted probability of recovering when you don't receive treatment and when you receive treatment with the observed one. So this is the one that we compute now. We essentially are going to approximate this from the data and then weight them by the proportion of young people and old people in the population, not in the control and the treatment group. And that's the important part. Because if you remember, the observed probability of recovering given that you're in the control group is distorted by the fact that the probability of being young if you are in the control group is lower than in the general population. And the probability of being young if you're in the treatment group is higher than in the general population, and that is the problem. So what do? We basically correct that term by replacing it by the true fraction of young people in the population or the true fraction of old people in the population. And again, this only works if you have actually observed the true conditional effect, which only holds under this conditional independence assumption. So let's visualize what's going on here. We have our population of young patients. We are treating more of them, and this is our problem. But now we're not going to mix them with the old patients. We're going to consider them separately. We're going to take a look at, so now we don't observe what happens when we don't treat for the patients that we treated, and we don't observe what happened when we treated, if we had treated for the patients that we don't treat. And we put everyone into a control and a treatment group, right like we did before. So this is exactly the same as we did before when we had mixed the young people and the old people, except that we're considering the young people separately. So now in our control group, we have these two young people. Before they were accompanied by many old people, and we see that all of them recover. So we realize that if you're young, you're gonna recover anyways if you don't get the drug. And we have many more young people in the treatment group, but now it doesn't matter because we're not mixing them with the old people, and we correctly observe that they all recover. What about the old people? And that gives us the true conditional probabilities of recovering if you don't receive the drug and recovering if you receive the drug, under this assumption that there's not additional confounding factors. Now for the old people, similar thing. So systematically, we are treating less of them, but now we don't care because we're considering them separately from the young people. So now we're not seeing the other potential outcomes and so on. This is the data that we're going to observe. The question marks are counterfactuals. Now when we consider the stratified data, these old people in the control group are not together with the young people, they're on their own, and this enables us to correctly see that none of them recover, that the true probability of recovering if you're old and you don't get treatment is 0. In the treatment group, now these two old people are not together with a lot of young people that boost the seeming likelihood of recovering, they're on their own. So we correctly see that half of them are going to recover if they receive treatment. And this corresponds to the true probabilities of recovering or not recovering, where depending on whether you receive treatment, if you are old. Because again, we're assuming there are no confounding factors. So now we can compute an adjusted causal effect where we multiply these probabilities by the true fractions of old and young people in the population, and we have managed to correct and observe that the true effect is that you have 0.5 probability of recovering if you don't get treatment, and you have 0.75 probabilities of recovering because if you receive treatment. And again, what we have corrected is the fact that here we're putting in 0.5, even though in the treatment group there's more young people and in the control group there's more old people. If we compare this to the observed effect, this is exactly what I just said. Remember that there's less young people in the control group, which drives down this probability of recovering if you're in the control group, and there's more young people in the treatment group, which drives up this probability of recovering if you're in the treatment group, which completely distorts the observed effect. It's very important, and this is why I've been repeating it almost in every slide, to remember that this only works under this conditional independence assumption if there are no additional confounding factors. Even if there are other confounding factors, it's probably still a good idea to at least try to correct and just state I've corrected at least for age or socioeconomic status or something else. But it's also important to realize that at the end of the day, if you don't have a randomized controlled trial, you cannot guarantee that you're observing the true causal effect. All right, so what have we learned? We have learned the definition of potential outcomes, which enable us to define these alternative realities and formally define what it is to have a causal effect. We have understood, hopefully, why randomization allows us to perform causal inference. We have defined confounders and understood why they can completely distort the observed effect in the data. And we have learned how to adjust for confounders and also when this works, under what assumptions we can adjust for confounders. And that's all I got. Thank you very much.